All right. Hi, everyone. Is the sound okay for the people in the back? Yeah? Okay, perfect, great. A quick practical reminder, because tomorrow we have the second practical session actually. So in case you have any questions about the first programming assignment or a research assignment, then please make sure to do come and do visit, because we will be there with quite a big team. And we will be able to answer all of your questions, most of your questions, if not all of your questions. Yeah, I see Jan. Of course, we cannot answer everything, but the things that, without giving away the answers, we will be able to help you with that. So today, there is going to be this mini lecture on gradient-based neural architecture search. And afterwards, we're going to have the first student presentations. So half of the group will stay here in this room, and half of the group will move to Huygens. So if you follow Jan, he's going to move there, then you should arrive in the correct room. All right? So then let's get started with gradient-based neural architecture search. So as we all know, deep learning methods are very powerful, but also they're very problem dependent. Like, there's no one-size-fits-all solution, and different problems require different neural architectures. So when we are presented with a deep learning problem, we have to answer or come up with the neural architecture that we want to use in order to solve this problem. And we have to answer questions like, how many layers do we want to use in their neural network? How many nodes do we want to use per layer? How do we want to connect these different layers, et cetera, et cetera. So there's like these tons of different questions that we have to answer in order to be able to solve a problem with deep learning. So it's not a simple out-of-the-box solution that you can apply to every problem, and this does require quite some engineering in terms of the architecture. So the question is, of course, how can we find a good neural architecture for a given problem? And a repeating theme throughout this course is that manual labor should be abstained from, like with hyperparameter tuning, also with neural architecture search. It's expensive, it requires expert knowledge, and also probably suboptimal, right? So we want to automate this, and more specifically, we're going to look at a way to automate this using gradient descent, because gradient descent has been widely successful in deep learning. And so the question is in this lecture whether we can also apply this in order to find good neural architectures. And we encounter a problem then, because many choices that you make when designing a neural architecture are discrete. So, for example, we have questions like, do we want to have a connection between two layers? Do we want to have an operation going from one layer to another layer? Or what operation do we want to use if we go from layer 1 to layer 2, for example? And with the discrete choices that we have to make, the problem is that these choices are not differentiable by nature. So there is no gradient signal that we can naturally use in order to optimize a given objective. And to see an example of this, suppose that we have a very simple network architecture. So we have layer 1 feeding into layer 2 by an operation 1. And operation 1 you can think of as something as simple like a fully connected layer. And now suppose that we want to ask ourselves the question, well, do we want to add another operation that also feeds into the second layer? And another way to pose this question, a bit more mathematically precise, would be to say that we're going to apply this, the second operation, so O2 here, and we're going to multiply this with alpha. So alpha is going to be either 1 or 0. So it's going to be 1 if we decide to use the operation, and it's going to be 0 if we decide not to use the operation. And this reflects our choice. So either we want to make alpha 1 and use the operation, or we do not use the operation, which means that alpha would be 0, right? And this resembles a step function that maybe you're familiar with from the deep learning course or maybe elsewhere, where we have this two flat regions. So either we do not use it and the line is 0, or we do use it and the line is 1. And the problem is that in this region, there is no gradient signal. Right? So it is not straightforward to actually use gradient descent for these problems. Now we're going to take a deep dive into one method that actually overcomes this issue, and that's DARTS, which was proposed in 2019 by Liu et al. And their idea is to relax the search space. So instead of trying to find a discrete architecture coefficient A, or alpha, we're going to allow it to be continuous. So instead of it being either 0 or 1, we're also going to allow it to range anywhere between these two values, at least a normalized version. So by doing this, we go from this non-differentiable function to a differentiable function, which means that we can actually apply gradient-based search. And that's what we're going to take a look at now for the remaining 15 minutes, roughly. So that starts. So to describe a bit more in detail the problem, so what we do in DARTS is we assume that we have some rough network topology, or cell topology, and that may look something like this. So every node in this graph corresponds to a layer. You can think of it as a layer. And on the edges, we perform certain operations. And operations could be, for example, convolutional layer, for example, fully connected layer, for example, element-wise multiplication, and so on and so forth. And initially, we do not know what operations we want to use in this network topology. So we do not know what operations we want to use. For example, a 3x3 convolution, 5x5 convolution, etc., etc. So the question is, of course, what operations do we want to use on every edge in this network? And the key idea of DARTS is just to say that we're going to have the set of different operations from which we can choose. So for example, we can choose, in this case, from a 1x1 convolutional layer, 3x3 convolutional layer, and 5x5. And then we're just going to say that we're going to mix these different operations along every edge. So the graph on the right here now becomes a mixture graph, where between every two nodes, we're going to place each of these three operations in our candidate set. And we're going to mix them using different weighting coefficients, or architecture coefficients. And you can kind of interpret them as the probability of using a given operation. And by applying DARTS, what we do is we learn these mixing coefficients, as well as the weights of the operations, and then we may end up with a trained mixture topology, which looks something like this. So the boulder lines, in this example, they receive the largest strength, and means that these operations were found to be very important by DARTS, whereas the thinner lines or arrows, they're actually found to be less important and receive less weight by DARTS. All right, so now let's see on the blackboard a small example of how this works. Let's see if we can put this a little bit up. So suppose that we have like one layer here. Sorry for the sound. And suppose that the activation in this layer is denoted by some x. And furthermore, suppose that we have a second layer here, which is layer 2. And what we do in DARTS is now we're going to have one edge from layer 1 to layer 2 for each of the operations in our candidate set. So in the example that we had before, we had a convolutional 1x1, convolutional 3x3, or convolutional 5x5. So for each of these, we're going to create an edge into this layer. Now it can go a little down. And for every edge, we're going to give a certain weight. We're going to assign a given strength of using this operation. And we denote this by alpha superscript 1, 2, because we're going from the first layer to the second layer. And as a subscript, we indicate which operation we're talking about. So in this case, this would be operation 1, or O1. So this would be, for example, the convolutional 1x1 operation. Then we are going to add another arrow for the second operation, again with a strength from layer 1 to layer 2, with a subscript indicating what operation this is. So this is operation O2. And we also do this for the third operation in our candidate set. So this is going to be, again, the strength from moving from layer 1 to layer 2. And this will be operation 3. So far so good? Yeah? Okay. And what we then do is we say that the output of going from layer 1 into layer 2 is going to be a mixture of these different operations. All right, so how we denote this is that the output, which we denote by O hat from layer 1 to layer 2, applied to our input X, is going to be a weighted combination of the different operations applied to our input. So this is going to be a weighted operation from 1 to 2 for every I, where I goes from 1 to 3 in our case, because we have 3 different operations. And with this weight, we're going to apply the ith operation to input X. Right, so we really take this weighted combination of these different operations, and every weight here, every weight I is simply a softmax over these different coefficients. So what this looks like is that Wi from layer 1 to layer 2 is just the softmax of all of these mixture coefficients. So this is A1, 2 for operation 1, A1, 2 for operation 2, and A1, 2 for operation 3. And then we're interested in just the ith component, so this will be the ith entry. So this is going to be the weight with which we're going to apply this operation. All right? So this is basically the softmax over each of these activation strengths, which ensures that they are actually defining a probability distribution. So that every weight, so the sum of these weights will be equal to 1. So that's what we're doing by normalizing these weights. Okay, and that's basically how DARTS works. So we have a candidate set of operations. We define this mixture graph over these different operations, and we mix them using these coefficients. So the learnable parameters, or hyperparameters, are then the operation strengths. But of course, you also still have the weights of these operations. Because even though we're only interested in searching for a good neural architecture, of course, also the weights are relevant for this. Because you could have a convolutional 1-by-1, which is the best operation to perform, but if the weights are totally random, then the operation is not going to make sense, right? So in DARTS, we actually jointly learn both of these parameters or hyperparameters. And then we should actually think for ourselves, like, what is the learning objective that we're yes, I see that there is a question. No, these are not the same weights. No, good remark, yeah. So these are really the normalized mixing coefficients, so really based on the alphas here. And the weights on the slide here, should have picked a bit better notation, but these are really the weights of the different operations. Very good remark, yeah, thank you. I see there's another question. No, they're actually, so the operation strengths, they're just scalars, so they're just single numbers. But because of this softmax operation, we actually normalize them to be between 0 and 1. And this also ensures that the sum of the different WIs will also be equal to 1. Yeah? You mean this weight? No, actually the only parameter that we have would be the alpha, but based on the alphas we actually compute them. So they're not free parameters, but they're actually just a normalized variance of these alphas. Yeah? Okay. Okay, so yeah. So the parameters that we want to learn are the architecture coefficients alpha, which are displayed here, and then also the weights of the operations, which are not equal to this. A bit of an unfortunate notation of letters, but okay. And we're trying to jointly optimize these two. So in the end, we are only interested in finding the best architecture, which minimizes the validation loss of our network. And of course, the validation loss depends on our architecture coefficients alpha, but also, of course, on the weights of our neural network. And what we do in DARTS is we say that we're going to optimize the architecture, assuming that the weights of the operations that we have chosen are optimal. So that we fill in here W star given this architecture. So these are the best weights of all of these operations, assuming that we have this architecture. Okay? And that's basically saying this. So these are the optimal weights under this architecture, which minimize the training loss. So again, we have this bi-level optimization problem, where on the training set, we are trying to find the optimal weights for the operations. And on the validation set, we are then trying to find the best architecture coefficients. And this also resembles what we have seen in MAML, for example. Now, of course, there is a question because computing the global minimum or the best possible weights is, of course, intractable. Because also when we're training just regular deep neural networks, we already know that we're not going to find a global solution, right? Or most likely not. So what can we do to resolve this issue? Any ideas? What do we do in regular deep learning? So we know that we're not going to find the global solution, not the globally best optimal parameters. So what do we do instead? Yeah. Yeah, trying different parameter settings. Any other ideas? Yes? Just gradient descent, exactly. Yeah, so instead of trying to find the globally optimal parameters, what we can do is we can just settle for local minimum, right? We can just settle for an approximation to the solution, which would just be a local minimum. And in the DARTS paper, they're actually as crude to just say that we're just going to do one gradient update step. So we're going to approximate these globally optimal parameters by just doing one gradient update step on our training loss. Right? And then they say this is an approximation to our optimal parameters. Yes? That's a good question, but actually I think this actually more generally applies to deep learning in itself, because we know that there are many local minima, and we probably know that with high certainty we're not going to find the global minimum, right? But I think what the success of deep learning actually points out is that despite the fact that we're not settling for global optima, and actually approximated with local solutions, so local minima, these local minima are actually quite good. So I think that the local minima actually are pretty good solutions to the problem at hand. So I think that's the main insight here. Does that answer your question? Okay. Okay, so we're going to make this approximation in DARTS for these optimal parameters using one gradient update step. Okay, And then, of course, the question is, well, how can we optimize this entire thing? So given that we have approximated this expression by just performing one gradient update step, how can we then optimize the outer objective, which is trying to find the best architecture? Any ideas on that? Yes? Yes, gradient descent, exactly. So we apply gradient descent both on the inner level in order to find good weights for the operations. And then we also apply gradient descent again on the validation loss, which is also what we have seen in mammal, in order to optimize the architecture coefficients then. And I see that I do have to speed up to make time for the student presentations. So in pseudocode, it looks like the following. So we initialize the mixture topology of our neural network. And then what we do is we're going to repeat this process of performing gradient descent on our architecture. So we're going to compute this gradient of our validation loss with respect to our architecture coefficients. And at the same time, we're also going to update the weights of our parameters. So at the same time, we're also moving our weights W just in the direction of the gradient, or opposite direction of the gradient on the training loss. So this is relatively similar to what we have seen in mammal, although there are some slight differences. And this is basically all that we have to do in DARTS. So we just sample a task, we perform gradient descent on the training set in order to update the weights of the operations. And once we have updated these weights, we're going to evaluate the eventual model on the validation set. And based on that loss, we're going to update the architecture coefficients. All right, so now lastly, what we do end up with within DARTS is a soft architecture. So we're going to have this graph where we have different strengths of using these different operations. But in some cases, it's beneficial to actually have a discrete architecture. So to know which operations we actually want to use, rather than how much we want to use the different operations. And to do this, we can simply select the top K operations from every layer to another layer, and in that way, discretize the architecture. So for example, if we only select the top one operation per pair of layers, we end up with this architecture. So we're just selecting the operation with the largest weight for every transition. All right, and now there is one problem. I wanted to skip over this because we are low on time. But one problem if we do this is that we have changed the behavior of the network. So because we have just removed and cut out some of the operations, of course the behavior of the neural network can be completely different. And maybe it's no longer a good solution to the problem that we had. So what this means is that we actually have to retrain this architecture afterwards. All right, and in practice, DARTS is often cheaper and has better or comparable performance to related methods. So comparing it to evolution-based architecture search or reinforcement learning architecture search, the search cost in terms of GPU days is often quite a bit better, while the test error is also often better or comparable. So in summary, this I will skip. As a limitation, I want to say that this also involves the computation of second-order gradients, which is expensive because it is quadratic in the number of parameters. But we can, of course, make first-order approximations. And also in their paper, they propose this neat trick to kind of circumvent the quadratic complexity. And lastly, we also, of course, have to define the rough network topology that we're dealing with. So that's a quick summary of DARTS.